All right, hey guys, Mr. Higdon here. Going to go ahead and solve some of these problems. We are going to solve problems 8, 9, 10, 11, 12, 13, 14, and 15. So if you are looking for help on a specific one of those questions, please go ahead and scroll to that question. I have my calculator up here so you get to see everything I'm going to do. Let's go ahead and let's get going. So question 8, Avril, a skateboarder, starts from rest and accelerates at 3.5 meters per second squared until she reaches a top speed of 13.4 meters per second. How far did she travel during this acceleration? So step 1 is going to be to list out our variables. I recommend having your equations nearby. I'm going to go ahead and write the equations up here, and I'm going to bring these with me. Equation 1 is going to be delta x equals v initial t plus 1/2 a t squared. Equation 2 is going to be v final equals v initial plus a t. And equation number 3 will be v final squared equals v initial squared plus 2a delta x. I'm going to be kind of bringing those around with me. Okay, so let's grab our variables. We've already written down the variables. Let's go ahead and say that from rest tells us that the initial velocity is 0 meters per second. We say that it accelerates at 3.5 meters per second squared. That's going to be our acceleration. And the top speed of 13.4 meters per second is going to be our final velocity. We're trying to solve for how far she traveled, so delta x is what we're looking for. And so we don't care about time for this problem. So we're looking for an equation that does not have time in it. We're going to use this one, the third one. Does not have time in it. I'm going to go ahead and get the equation out of the way. Go ahead and copy the equation. We always want to make sure that we start with the equation that we are using and go from there. So v final is 13.4 meters per second squared. Starting velocity is 0 meters per second squared. We have 2 times 3.5 meters per second squared times delta x. We can go ahead and switch colors here. I'm going to get rid of that guy right there. 13.4 squared is going to give us 179.56 meters squared per second squared. And then 2 times 3.5 is going to be 7 meters per second squared delta x. Let's go ahead and let's switch back. We're going to divide both sides by 7 meters per second squared. And we get our answer of delta x equals 179.56 divided by 7. 25.7. And the units work out, the second squared gets canceled, and then one of those meters gets canceled, so we have meters. Okay, let's move on. A car is braking to a quick stop. If the car was traveling at 25 meters per second and can brake with an acceleration of 3 meters per second squared, since we're braking, I'm going to take that 3 and make it a negative 3. I want to know how far does the car travel while stopping. So once again, we're going to be solving for delta x. Extra bit of information there. We were told that it comes to a quick stop. So let's grab our variables. We have an initial velocity of 25 meters per second, a final velocity of 0 because we are coming to a stop. The acceleration is going to be negative 3 meters per second squared. I put a negative there, remember, because we are braking, and so we want to make sure that we're showing a negative rate of change of velocity. We're looking for delta x, and so once again, we do not care about time. We're looking for a distance. So we take a look at our 3 equations, and we say which one are we going to use, which one does not have time in it, and we're going to choose that bottom one. Once again, so we're going to use equation 3. I'm going to go ahead and lasso that and duplicate it. Copy that over. and then bring those down for the next question. Cool. Let's go ahead and plug in some values. V final is 0 meters per second. That's all going to be squared. Equals 25 meters per second squared plus 2 times negative 3 meters per second squared times delta x. Let's go ahead and simplify this a little bit. 0 is just going to be 0 meters per second, and both of those are squared. Then 25 squared. Whoops. (625) meters squared per second squared. And then we're going to go ahead and multiply 2 times negative 3. So we're going to get negative 6 meters per second squared times delta x. Let's get that 625 onto the other side. Minus 625 meters per second, both squared. And then we have negative 625 meters squared per second squared is equal to negative 6 meters per second squared times delta x. And we're going to divide both sides by that negative 6 meters per second squared, negative 6 meters per second squared. Just like the previous question, the seconds squared goes away, and one of the meters goes away. That gets canceled. Sorry, getting a little squished right there. And so we're left with delta x is equal to 625. I'm just going to go ahead and use the history there. Negative 625 divided by negative 6 is going to give us a positive number, and it's going to be 104.17. The units are meters. Awesome. Let's move on. Ben Russian, haha, get it, is waiting at a stoplight. When it finally turns green, Ben accelerates from rest at a rate of 6 meters per second squared for a time of 4.10 seconds. Determine how far Ben traveled during this acceleration. Okay, first step, as always, let's list out our variables. We are told that Ben accelerates from rest. He's waiting at the red light. Initial velocity is 0. At a rate of 6 meters per second squared, so that tells me the acceleration, 6 meters per second squared. And we are given time. He is stepping on the gas for 4.10 seconds. We are looking for delta x. We want to know how far Ben travels. And so we don't know what v final is, and we don't care about v final. So we're looking for an equation without v final over here. And I see a v final here, I see a v final here, so I think this is the equation we want to use. Let's go ahead and copy that over. And I'm going to bring these down for our next question. Okay, let's do some math. We have delta x, and that's nice. It's over there on the left side. We're not going to have to do too much algebra. We just got to plug and chug. The initial velocity is 0, so I hope you're okay with me just saying that that's all going to just be 0. We don't care about that. And to that, we're going to add 1/2 times the acceleration, which is 6 meters per second squared, and then the time, which is 4.10 seconds. That's going to be squared. So delta x is going to be equal to, let's go ahead and multiply the 1/2 times the 6. Let's get 3 meters per second squared. Multiplied by, and we're going to do 410 seconds squared. Sorry, 4.10 squared. 16.81 seconds squared. Make sure that you include that square on the seconds. I'll show you why in a moment. So since we have the seconds here squared and the seconds down here squared, those go away, and would you look at that, we're left with units of meters. So let's go ahead and rewrite this as delta x is equal to whatever 3 times, sorry, I'm not used to using the calculator on the iPad. 3 times our previous answer of 16.81, and we get 50.43. And we're left with just meters, and so that is going to be our answer. All right, let's move on. Rocket-powered sleds are used to test the human response to acceleration. If a rocket-powered sled is accelerated to a speed of 345 meters per second in 1.44 seconds, then what is the acceleration of the sled? So we are going up to 345 meters per second. And the implication for this problem is the rocket-powered sled is being accelerated up from rest. So very, very, very fast. Big acceleration. Let's go ahead and let's figure this out. So let's list out our variables. We're solving for acceleration here. Delta x, v initial, v final, a, t. That is a b. There we go. Awesome. So we are from rest, 0 meters per second, to a speed of 345 meters per second, and then a time of 1.44 seconds. Awesome. We're looking for acceleration. We do not care about delta x. Let's go ahead and cross that out. And so we're looking for an equation that does not have delta x in it. If we look over here at our equations, equation 1 has delta x, equation 3 has delta x. Let's go ahead and use equation number 2. So I'm going to go ahead and lasso that. Make sure not to grab anything I don't want. We'll bring that over, and we'll bring these guys down for the next question. Okay, let's plug and chug. V final is 345 meters per second. V initial is 0. Acceleration is our variable we are interested in, and time is going to be 1.44 seconds. Simplify a little bit. Let's get rid of that 0. 345 meters per second is equal to 1.44 seconds times a, and let's divide both sides by 1.44 seconds. Notice how the units work out. We have 345 meters per second divided by a time in seconds, so our answer is totally going to be in units of meters per second, which we can rewrite that as meters per second squared. And let's figure out what our value is. 345 divided by 1.44. And we get our answer of 240, just under 240, so 239.6. All right, let's put that in a box. Let's move on to part B. So we're assuming the same situation, same sled, same acceleration. What is the distance that the sled travels? So this time around, let's go ahead and I'm going to copy down my variables, and I'm going to erase delta x, and I'm also going to go ahead and copy down the acceleration we just solved for. So just because we have two different steps we're working with here, doesn't mean that the acceleration is going to be different. So we can use the acceleration that we just got, and maybe that'll make our life a little easier. So we're looking for delta x. That is going to be our question mark. And we consider our equations. We have v initial, v final, a, and t. So we're actually going to have two choices. We can use either this first equation, or we can use the third equation. This equation isn't going to help us. We've already used that. I think the top equation is going to be easiest, mostly because the v initial right there is going to be 0. And so we're going to have a really easy problem to solve. Let's get rid of all this clutter. And let's copy that equation. Okay, let's plug in our value. Delta x is what we're solving for. That's nice. We don't have to do any algebra to get it. V initial is 0, so I'm just going to put a 0 right there because anything times time is going to be 0. And to that, we're going to add 1/2 multiplied by the acceleration, that really big number from the previous part, 239.6 meters per second squared. And then we're going to put in the time of 1.44 seconds, and all that's going to be squared. Let me go ahead and lasso all this and get it down there for the next question. Okay, I'm going to go ahead and do delta x is equal to 1/2 times 239. So I'm going to do 239 times 0.5. I could also do divided by 2, same thing. So I have 119 0.8, and the units are still there, meters per second squared. That's going to be multiplied by 1.44 squared. 2.07 seconds squared. Alrighty. If we take a look at what we've got, the seconds are going to cancel out, and we're going to be left with meters, which we should. We're getting a delta x. So let's plug that into our calculator. I keep hitting stuff over here. I'm sorry. If you watch that and that's distracting, I apologize. 119.8 multiplied by what we already have in our answer there, 2.07. 248.4. 248.4, and the units there left over are meters. That checks out. We are happy physics students. Awesome. Let's move on to 12. At a sports car rally, a car starting from rest accelerates uniformly at a rate of 9.0 meters per second. So we have an acceleration, we have this idea from rest, and a distance of 100 meters. The record time to beat is 4.5 seconds. Does the driver do it? So we are going to solve for a time, and then we're going to go ahead and compare it and see if it's shorter than 4.5 seconds or if it took longer than 4.5 seconds. If it's longer than 4.5 seconds, that means if they didn't get the record, what acceleration do they need? So if it wasn't quick enough, obviously they aren't getting as much acceleration as they need to. So we have to boost that 9 meters per second squared to be a bigger number. So let's first solve for time. Let's see if they beat the record. Let's list out our variables. Delta x, v initial, v final, a, t. The delta x is going to be 100 meters. That is how far it travels. The initial velocity is 0 because we are starting from rest. And the final velocity we don't know. The acceleration for this first part is going to be 9. Let me make that clear. 9.0 meters per second squared. And the time to beat, we're not going to put in that 4.5 seconds because we're going to solve for a time and then compare it to the 4.5 seconds. So we are looking to solve for t, and we don't care about v final. So let's go ahead, let's look at our equations. And we're finding something that doesn't have v final. I see v final here, I see v final here. I think that first equation is going to be our friend. Let's go ahead and let's copy that down. And let's move these guys out of the way. We might need them again for this problem, just in case we don't get the record, which I guess, spoiler alert, we don't. All right, let's solve this problem. Let's see what our time was. So delta x was 100 meters. That's going to be equal to, since v initial is 0, I'm just going to put a 0 right there. Anything times 0 is 0. And then we have 1/2 times their acceleration, which was 9 meters per second squared, times time squared. Now, I see that time squared, by the way, and I just know ahead of time that we're going to have to take a square root. So we have 100 meters is equal to 4.5 meters per second squared, all that multiplied by time squared. And we are going to be dividing both sides by 4.5 meters per second squared. Wow, I'm really kind of going nuts over here on the calculator. I'm going to do 100, and I'm going to divide that by 4.5. And we get 22.22. 22.22. And the units here, these meters are going to cancel, and we're going to be left with seconds squared on top, which is a little weird. But this is equal to time squared, remember? And so what we're going to do is we're going to take the square root of both sides to get that time alone, and that seconds is going to, the seconds squared is going to turn into seconds. So I'm going to go ahead and take the square root of 22.22, and we get 4.71. 4.71 seconds is our time. So do we get the record? Nope. We are 0.21 seconds too long. So what we need to do instead is I'm going to take all of this and I'm going to squish it over here. We're going to just set that aside to make sure that we have room. I'm going to reimagine these variables, and we are going to see exactly what acceleration we needed in order to get the record. So I'm going to move them over here. A little cluttered, but that's okay. So now we are still in this 100-meter race. We're still starting from rest, but we don't know what acceleration we need. But we know we have to complete that 100-meter race in 4.5 seconds. So since nothing has changed about what we don't care about, that is, we don't have v final, we don't need v final, let's go ahead and let's use the same equation that we did before. Delta x equals v initial t plus 1/2 at squared. You can go ahead and toss that right there. And, looks like I forgot the bottom of the triangle on the delta. All right, it's a little cramped, but that's okay. This v initial t is still going to be 0, so I'm going to plug in 100 meters equals 0 plus, and then 1/2 the acceleration is what we're looking for, and we have 4.5 seconds squared. We're going to plug in the world record. 100 meters equals 1/2 times 4.5 is 2.25. Oh, I'm sorry. I almost made a mistake. I need to make sure I square that. So I'm going to take 4.5 and I'm going to square it. I get 20.25 seconds squared. Multiply that by acceleration. That's our variable. And we're going to go ahead and divide both sides by 20.25 seconds squared. And would you look at our units? They're going to give us units of acceleration, meters per second squared. So while I'm over here typing things in the calculator with my right hand, 100 divided by 20.25, we are going to get oh my goodness, I'm so sorry. We still have a 1/2. We need to divide 20.25 divided by 2 because my mistake, I forgot about that 1/2 right there. Been doing all these problems and look at that. Rookie mistake. Let's go ahead and replace that 20.25 with 10.125 seconds squared. And then we are going to divide both sides by 10.125 seconds squared. And we get an acceleration of 9.87. So I'll say 9.88 meters per second squared. And that's going to be the acceleration we need. So notice, previously, we didn't get the record with 9 meters per second squared, but we would get the record if we go a little bit, if we accelerate at a greater rate. Awesome. Let's go ahead and move on. A jet plane lands with a velocity of 100 meters per second and can brake at a maximum rate of negative 5.0 meters per second squared as it comes to rest. Awesome. So that tells us that our final velocity is going to be 0. Can this plane land at an airport where the runway is 0.8 kilometers long? 0.8 kilometers is the same as 800 meters. So once again, just like the previous question, don't plug in that 800 meters because we don't know if that's a realistic number. Instead, let's go ahead and solve for how much distance the jet plane needs and compare that to 800 meters. So solve for delta x and compare to the runway length, 800 meters. So that's going to be our plan. I'm going to go ahead and get rid of this little annotation here. First step, let's list out our variables. Delta x, v initial, v final, a, t. What do we know about the jet plane? Jet plane lands with a velocity of 100 meters per second, has a final velocity of 0 meters per second because it is coming to a stop, and it experiences an acceleration of negative 5 meters per second squared. We're looking for delta x. We want to compare that to the 800 meters. We do not care about time, so we're looking for an equation without time. That is the Rosemary equation down here. Equation number 3. No time. The other two have time here, here, and here. So let's go ahead and lasso that. Bring it over here. And let's solve for delta x. And let's see if it's bigger or smaller than 800 meters. V final is 0. That's going to be equal to 100 meters per second. All that squared. And to that, we're going to add 2 times negative 5 meters per second squared times delta x. I'm going to go ahead and put these all in parentheses just so we remember that they're all multiplied together. All right, let's go ahead and replace some things. We've got 100 times 100. It's going to be 10,000 meters squared per second squared. And I'm going to do a minus there because we have the negative 5 times 2. So minus 10 meters per second squared times delta x. So let's go ahead and get that delta x and its coefficient there on one side. Let's subtract the 10,000 meters squared per second squared from both sides. A little cramped, my bad. Those go away. And we're left with negative 10,000 meters squared per second squared is equal to negative 10 meters per second squared delta x. And so now we need to divide both sides by that coefficient on the delta x. Divide both sides by, whoa, don't want to cover up the seconds. Negative 10 meters per second squared. Negative 10 meters per second squared. Bah, bah. And let's take a look at what happens to our units. The seconds go away. Seconds squared is on the bottom of both of those. And then this meter is gonna take care of one of those meters. So we're gonna end up with meters. Negative 10,000 divided by negative 10 is gonna give me just 1,000 meters. That's gonna be my delta x. And 1,000 meters is certainly larger than 800 meters. So no, we do not have enough room on this runway. They're gonna have to land somewhere else. Awesome. Let's go ahead and bring our values down. Ba-ba. Okay. A car starts from rest and takes 5 seconds to uniformly accelerate to 30 meters per second and then travels at 30 meters per second for another 10 seconds. Calculate the distance the car travels in those 15 seconds. Okay, so I gave you a little bit of an interesting question here. 15 seconds is the combination of the traveling at a 30 meters per second and the 5 seconds it took to uniformly accelerate. So this is a 2-part problem. Let's go ahead and let's draw this out real quick. So here's the car. This is the car getting faster. Sorry for the handwriting. And that's the car moving really fast. So this is going to be 1 delta x. We're going to have to solve for that delta x first. And then we have the car traveling at a constant speed. And that's going to travel another delta x. Whoop, I want to make sure I have the same amount of speed lines. So we have 2 delta x's we were solving for. One of them where there is acceleration, and one of them where there is not acceleration. Let's go ahead and let's solve these in pieces. I'm going to go ahead and bring our beautiful diagram, and I'm going to go ahead and shrink it quite a bit, if you don't mind. Okay, so let's go ahead and let's solve for this first delta x, the delta x of getting faster. Let's write out our variables as we do every single time. And we know we're going to be solving for delta x. So what do we know about this situation? The car is starting from rest, so we have 0 meters per second. The final velocity is going to be what they told us over here, 30 meters per second. We do not have an acceleration, that's our question mark, and we have a time of 5 seconds. So this is an interesting situation. We do not have an acceleration and we do not have a delta x. If we wanted to solve for delta x right away, none of our equations are missing acceleration. They each have it. So how about this? Let's solve for acceleration first. Then solve for delta x second. We can use our acceleration we solve for to get delta x. So let's do that first. Let's solve for acceleration. We have a v initial, a v final, and a t. I think this equation is going to be our best friend here. That's a really nice equation to use. So V final equals V initial plus A times T. Oh, I guess I didn't copy it this time. That's okay. V final is 30 meters per second. V initial is 0 meters per second. And acceleration we do not know, but we know it happened over 5 seconds. Let's go ahead and let's work this out here. I'm going to simplify down a little bit. Get rid of the 0. We have 5 seconds times A. And we are going to divide both sides by 5 seconds. 5 seconds. Those go away. Since we have meters per second over seconds, we are going to get our answer as expected. We're going to get an A value that is in meters per second squared. And the answer is going to be 30 divided by 5, which is 6. So that is our first step. We have 6 meters per second of acceleration. Let me put that in there. 6 meters per second squared. Awesome. Now we can solve for delta x. Let me go ahead and grab this and bring this down here. So that's solving for acceleration. Now get delta x. I'm looking for an equation that has delta x in it, and let's try and make our life as easy as possible. I see, since our initial velocity is 0, this equation right here, this first one, is really nice and easy. Since our v initial is 0, that is just going to be 0. And so let's go ahead and start there. Let me lasso the problem. Oh, let me see if I could not get that blue underline. Ha-ha! Look at that. Talent right there. So let's solve for delta x. That's what we're looking for, so we're going to keep that there. The initial velocity is 0, so I'm going to have that whole thing and replace with 0. We have 1/2 times the acceleration, which we just solved for, which is 6 meters per second squared, times the time, which is 5 seconds squared. Let's go ahead and continue solving for delta x here. 1/2 times 6 is going to be 3, and the units are meters per second squared. And we're going to multiply that by 25, which is 5 squared. And let's make sure to include the second squared there. So the second squareds go away, and I'm going to be left with the unit of meters, which is exactly what we want. We want a distance. So let's multiply 3 times 25. That's going to give us 75, and our units are meters, and that's going to be our delta x. But remember, that is the delta x for this, 75 meters. That's what we got there. So then how do we do this one? Let's go ahead and let's list out our variables and see where that takes us. I'm going to go ahead and scrunch all this down. We really did not give you enough space for this problem. This thing's a beast. Okay, let's squeeze it down. So once we're at 30 meters per second, we then travel at 30 meters per second for another 10 seconds. So do we have acceleration? No, we do not. That means that I can use this equation right here. Delta x, v, and t, that is something from last unit. And we can get our delta x from the information we have. It's coasting at a steady 30 meters per second, and it's moving for a total of 10 seconds at that constant speed. And so let's just solve. Delta x equals vt, that's going to be our equation. Delta x is what we're looking for. Velocity is 30 meters per second, and the time is, let me get that over here. The time is 4:36. Haha, just kidding. It's going to be 10 seconds. The units of seconds go away, and we are good to go. So then the resulting total delta x, let's get rid of that. Delta x total is going to be then, let's go in order here, 75 meters plus 300 meters, that's going to be 375 meters. And that's what we've got for the answer key. Awesome. On to the last question. Let's take a look. Let me erase all the annotations that we have on here, all the underlines, all that stuff. A car travels at 30 meters per second for 5 seconds. The driver sees a deer and slams on the brakes. It takes 2.4 seconds for the car to come to a complete stop. Calculate the distance the car travels in those 7.4 seconds. So let's take a gander at what we got here. We once again have a car that is traveling at a constant speed. So we'll write that down. Constant velocity of 30 meters per second until a deer jumps out into the road. Let me see if I can draw a deer here. Eyeball, smiley face. It's a happy deer. And it jumps out. I did not go to art school. And the deer says, "Whoa, hold on, don't hit me." And the car, which doesn't want to hit the deer, is going to slam on the brakes. And so the car is going to be like, "Whoa." Wait, no, that's not how a braking car would look. The braking car would be like, "Whoa, watch out here." So it's still moving pretty fast, but it's going to hopefully come to a stop and magically get smaller. I hope you guys at least get a laugh out of this. This is terrible. This is just some beautiful artwork. So we have two different segments. We have a constant velocity segment and we have a braking to a stop segment. This side, acceleration is 0 meters per second squared because we're moving at a constant speed. And over here, acceleration will not be 0 meters per second squared because we're definitely braking. So let's do this first part first. Let's solve for this delta x up here, and then we'll solve for the delta x over here, and we'll add those together, and that'll be the total distance. Alrighty, part one, delta x, v, and t. Since we're at a constant velocity, we can use our skills from last semester. 30 meters per second, sorry, not last semester, last unit. 30 meters per second for 5 seconds. We have a pretty straightforward problem. 30 meters per second, 5 seconds. And we can do delta x equals vt and get 30 meters per second. Whoa, that's not an m. Times 5 seconds. We get a delta x of, seconds go away, 150 meters. Sweet, okay. So that's how far the car was going in that first part. The second part, braking to a stop. Let's list our variables. Delta x, v initial, v final, a, and t. Classic. We're looking for delta x. We want to know the total distance travels, and then we're going to add that to the 150. The initial velocity is that starting 30 meters per second. The final velocity is 0 meters per second. Hopefully you stop before the deer. We'll keep him nearby just to remind us of what we're doing all this for. Yeah. Oh, oops. He got a little extra line in there. Boop. There we go. There he is. What a cutie. The acceleration. Do we know the acceleration? Nay. But we also know the time, 7.4 seconds. Whoop, I'm sorry. The driver sees a deer and slams on the brakes. It takes 2.4 seconds to come to a complete stop. So notice, just like the previous question, we don't have an acceleration. And in each one of these equations, there is an acceleration. So how about this? Let's solve for acceleration first, and then use that to solve for our delta x, just like we did in the last question. So let's solve for a. We are going to ignore delta x for now. And we are looking for an equation that has a in it, vf, vi, and t. I think this equation is the one for us. So v final equals v initial plus a t. Let's figure out what sort of acceleration we've got. V final is 0 meters per second. V initial is 30 meters per second. Oh, that doesn't need to be in parentheses. It's been a long video so far. And to that, we're going to add the acceleration times the time of 2.4 seconds. Okay, in order to get my acceleration alone with that 2.4 seconds, we're going to subtract 30 meters per second from both sides. And then we need to divide both sides by 2.5 seconds. 2.5 seconds. Notice the units here. We get meters per second. That is exactly what we're looking for. We get 30 divided by, 30 divided by 2.5. And I get 12, but don't forget about that negative. So we'll get negative 12 meters per second, which is meters per second squared. Awesome. I'm going to go ahead and put that negative 12 meters per second squared there in the variable list, because now we want to solve for delta x. So let's go ahead and take a look at what options we have. We can use this equation. This one already has delta x on the left side there. This one we can use as well. I think we used equation 1 last time. Let's go ahead and use equation 3. Let's use the Rosemary equation. So let's go ahead and let's move everything over. Oh, we're going to bring the deer with us. Whoa. Cool, that works. We're going to bring this on all over here just to keep ourselves organized. So the top was the constant velocity, and now the bottom is the acceleration. So we're going to use v final squared equals v initial squared plus 2a delta x, and we're going to use our variables from before. So let's go ahead and let's plug in v final is going to be 0 meters per second. All that's going to be squared. V initial is going to be the 30 meters per second squared, and we're going to take 2 times acceleration. We just got that. That's the negative 12 meters per second squared times delta x. Not the best x. Okay, let's simplify this a little bit. 0 squared gives us 0. 30 squared, jeez. 30 squared is going to be 9,000. Oop, 900, my bad. Meter squared per second squared. And then that we're going to subtract because this negative sign is going to be there. So we're going to do minus 24 meters per second squared times delta x. Okay, we cannot do 900 minus 24. Don't make that mistake. Take a look. We also have like incorrect units there. So we're going to subtract 900 from both sides. And we're left with negative 900 meters squared per second squared is equal to negative 24 meters per second squared times delta x. And let's go ahead and divide both sides by negative 24 meters per second squared. One of the meters cancels and the seconds squared cancels, and we're left with 900 divided by negative 24. Sorry, negative 900 divided by negative 24, which is going to give us positive 37.5. Awesome. So then we take a look at what our goal was. Our goal was to figure out the total distance traveled while you're braking. This distance traveled was the 37.5. And the first distance traveled was our very first 150. So the delta x total is going to be equal to that first 150 meters plus the 37.5. And what's a video without me accidentally clicking something on the calculator? 187.5 meters. That's not a 5. That's total distance traveled, and looks like we match the answer key. All right. Well, hopefully you guys got a little bit of benefit out of this video and you enjoyed my beautiful drawings. I will see you guys next week. Bye.